Wonderful. Today we have Julia Mundy, who will be doing the Wednesday night seminar to tell us about the design and construction of outside properties.
Great. Okay, so thank you all. It's a pleasure to see you all. Some of you who I've seen 2 hours ago, but nice to see you again. Some of you who I've seen earlier. So today I want to share with you just a really high level overview of the work that my group is doing on designing new materials. So on the title screen here, I have an atomic resolution image of one of these materials that I have synthesized. So the first really exciting part of the research is that each of these dots is an individual atom. So one aspect, okay, I've already gone on about this today, another round of this, but each of these dots is an individual atom. So this is really fun because we're able to image these materials with atomic scale resolution. In addition, we're not able to just observe what exists, but we're actually able to control. So this is a material that I have made. The brighter atoms here are lutetium, that's one element on the periodic table. The kind of lighter atoms here are iron atoms. And this is a material that I engineered and I synthesized, where I strategically went with 9 periods of a certain material and then put these double iron layers in there. And so we're able to engineer such a material that does not exist naturally and to be able to control the functionality. And then the really cool thing about this material, if you look at it, is that in fact, these atoms don't just sit in perfect flat planes. But if you see this, you can see that the atoms go up, up, down, up, up, down, up, up, down. And these distortions are picometer distortions. This is about 40 picometer distortion. And it turns out that the magnitude of this distortion directly impacts the magnetism, the magnetic properties in that adjacent layer. And so in this way, we're not only able to kind of control where we put atoms down, but we're further able to control with picoscale resolution the structure of the materials, which can have profound impacts on the properties. So I think this is really cool. I think this is some of the finest control of materials that you can have by any technique. And we're able to utilize this both to learn cool physics about these materials, as well as your new materials. This is something I'll show later, but is of interest to Intel for next generation memory devices, applied and fundamental. That's kind of the high level. So if anyone falls asleep, you got the punchline for this. It's going to be more than 5 minutes. So. Just don't lean back into that thing, because I did that the other day and it starts shooting out all the, I got coated my whole like shirt with that by accident. Oh, Elizabeth, I think there's some chairs over here. You want to come around? Just don't trip over my cord here.
We'll try my best.
Okay. So the first thing that I just wanted to say, for anyone who's taking kind of Physics 191 or an advanced class, these are examples that you might have seen. So the first one is actually something that Bob was relating to earlier, the fractional quantum Hall effects that's observed in these gallium arsenide heterostructures. The other example is high temperature superconductivity. The details of these are not important, but I just wanted to flash these up. These were 2 discoveries that won the Nobel Prizes. This one is an oxide material, so very similar to the chemistries that I make. This material was grown by molecular beam epitaxy, the same technique that I use. And both have tremendous relevancy and kind of continue to drive research agendas today. But kind of to the point of what we were discussing, both of these were observations that were made experimentally that completely shocked the entire physics community. So neither of these observations, either that one would get this fractional quantum Hall state, the Hall state was predicted, but that one could have this kind of fractionalized particles, or that you could have superconductivity emerge at high temperatures. There was no kind of theoretical framework for that. With superconductivity, it was discovered in 1911. There was a Nobel Prize in the 1950s. It was a solved problem. But it was really the existence of these materials and the experimental observation that completely revolutionized physics. So I always feel a little need to stand up for myself as an experimentalist, that it's not that just the theorists have the cool ideas and then, 50 years later, we prove them correct, but that really kind of these experiments and the existence of these new materials revolutionize the field and continue to reverberate in the field 30 years later. So, you know, details of this exact experimental observation, not relevant, but just really to say that new materials can be a conduit for fundamentally new physics, including new physics that we have no existing theories for, and that experimentalists can make cool discoveries and really kind of rock the world. So, okay, that's just a stand up for this. All right, so so specifically, the types of materials that I'm interested in are these families of quantum materials. And so what we mean by these types of quantum materials is we mean materials where quantum mechanics has an impact on kind of macroscopic length scales in the material. So in some sense, all materials are quantum materials. This chair is a quantum material because this chair is made up of atoms, and atoms stick together in chemical bonds because of quantum mechanics. Okay, so there is, at a very, very, very fine length scale, quantum mechanics happening in this chair. Okay, but if you wanted to describe the properties of this chair, you often don't resort to quantum mechanics. You might use classical mechanics if you wanted to throw it across the room or something like that. But quantum properties of the chair, not usually relevant to describing the properties. Okay, but we're very interested in these types of materials where we can observe effects of quantum mechanics even at kind of macroscopic length scales, and whereby we need to resort to these pictures beyond in kind of solid state picture, single electron picture, to be able to describe the properties of these materials. And so, as we can see, it is really a wide range of properties that can emerge in these types of materials. These include some of the more, I would say, mundane properties like conductors. Okay, copper wire conductors, different types of metals. Ferromagnetism is a really cool one. It's actually, you need quantum mechanics to understand the theory of it, but ferromagnetism was known by the ancient Greeks, so that's something we've known for quite a while, as well as some of the more really cool emergent properties, such as some of these topological phases, superconductivity, nonlinear optical properties, etc. And so my group's research interest is both in understanding some of these really cool phenomena in more detail, but also in engineering new materials that have enhanced properties, that display these properties, that allow us to kind of build devices where we couldn't before. Okay, so just to kind of flash up some more words, there's lots of just like words on these slides, but really the idea is that all of the properties that I've mentioned on the prior slide, we can think about exploiting them for some type of application. So our research really does have dual goals, kind of 1 foot in both doors, both trying to do fundamental science, but also thinking about materials that have particular applications. And a particular kind of driver of this is energy applications. So we're kind of a lot of the things that we're both directly looking for kind of power transmission. Can you make power lines that lose less electricity getting from the power station to your home? Okay, but also can you make computing devices that consume less electricity? So right now, computing is a sizable but not massive part of our global energy budget. I think maybe 8% or something like that of our global energy budget is used up by computing. But it's thought over the next 10 years that will explode, okay, with all of these Internet of Things and machine learning and server farms and, you know, everybody putting their dishwasher on the internet and all of these various different things, that it could even go all the way to 30% of our global energy budget. So really thinking of ways to compute, even thinking of more subtle aspects of that in how you transmit power around in a server, kind of one of these large facilities that Google or somebody else uses, really can have profound impacts on our global energy budget. So we're really interested in lots of applications, but particularly those driven by kind of lowering our global energy consumption. Okay, so I want to show you kind of what these materials actually are that we're interested in, and then how we combine them to make new functionality. So this is kind of a canonical crystal structure. So those of you hearing me talk about crystals in 195, so we're looking at a periodic arrangement of atoms, okay? And I've color-coded these atoms just to correspond to various kind of 2 distinct spots in this crystal and different elements that can occupy this site on the periodic table. So we think of these structures, these kind of AbO3 structures, perovskite, where this is an A site cation that's sitting here. Okay, these are mostly ionic materials. There's a B atom in the center, and then it's being surrounded by a cage of 6 oxygen atoms. Okay? So the name perovskite comes from actually calcium titanate. You can go check it out in the Museum of Natural History across the street. There's perovskite, it's calcium titanate. You can dig it out of the ground. It's kind of one of the most common of these materials. But what is really cool is that this is a very versatile crystal class, and almost every single element on the periodic table can be found in the A site or the B site or both. You know, in various different permutations and with various different other elements. And so one of the reasons that we're so excited about this class of materials, the oxides, is that you can really play with the entire periodic table. You have an enormous range of electronic, magnetic, and optical properties that I showed on the last slide, but you have the same structure. So you have this same template, the same structure, this common structural motif. So some of these structures, of course, have distortions. Okay, so they don't all have the perfect cube. Okay, they kind of tilt back and forth, but nevertheless, you have this common kind of oxygen octahedral cubic symmetry. Okay, and so that allows you to think about not only I want to search in kind of a single material, but that I want to combine materials together and search for novel functionality that might emerge in the interfaces between those materials. Okay, so once again, lots of words which are not hidden. But the first thing is this is a kind of a phase diagram showing what electronic and magnetic properties can be found in this example of these cuprate materials, these copper oxide materials I showed on the first slide. And so the x-axis here is what we call doping. But what that is physically in the experiment is taking a strontium 2+ ion and replacing it with a lanthanum 3+ ion. So you're varying the chemistry as you go across the series. The x-axis is temperature, so we can see that some of these really cold quantum phases only emerge at lower temperatures. And so one of the hallmarks of these materials is that really small perturbations can have profound impacts on the properties. So you can go over here from an insulator to a superconductor, so material that not only conducts electricity, but conducts electricity with zero resistance, perfectly zero resistance, all the way to a metal on the other side, just by making changes of maybe 5% substitution of atom A for atom B. You've got a chair over here. So this is one. Just don't trip over my cord, not my computer on the floor, and then you're not welcome. Okay. Yeah. So that's one of the hallmarks of these materials is that actually really small perturbations. You don't need to do a lot to go from a metal to an insulator. Okay, you need to do very little. However, if you're thinking about bulk crystals, okay, just kind of single chunks of material, that's the main kind of knob you have as experimentalists, the chemistry. Okay, so this is the type of synthesis you may have done in high school. If you like put some powder in a I don't know, crucible, and then you put a Bunsen burner flame under it and cooked it and it did something. Is that anyone do this in chemistry? Like made something? Yeah, right. Okay. So, it's also if you're making a cake, right? Same idea. But you're just kind of pouring everything together in the same can, heating it up, and maybe having a chemical reaction, but going from A plus B to AB. Okay. But you're just doing this macroscopically with, powders and everything like that. So that's kind of your main knob, your main control knob you have over your material. It's just what elements to put in there in what ratios. Okay. And how you just some of the details. In contrast, since I mentioned to you, we have all these materials that all have the same structure, and even more so, they have the same lattice constant. So the spacing between the atoms is quite similar. We can think about not only thinking about one material, but thinking about stacking materials on top of each other. And so now we can have these ultra clean interfaces, okay, where we not only can think about material A and material B, But we can think about, moreover, the interface between this material as being a new playground to stabilize emergent functionality. Okay. And I'll just give you some of the cool knobs that you can play with. So if you've heard of graphene, anyone? Yeah, okay, I know you have. But if you've heard of graphene, so graphene is a two-dimensional sheet of atoms. It's just a monolayer of graphite, just one plane of graphite. And what has kept many people, including the Kim group, very busy for many years is that graphene has fundamentally different properties of graphite. And moreover, two sheets of graphene, okay, can be different than one sheet in different twist angles. So that's a really fun game you could play with graphene, because even with Scotch tape, you can rip one sheet of atoms off of graphite. For a lot of the materials that we're working with, these materials are very strongly bound in all three dimensions. It's not possible to rip a sheet of atoms off, okay, because they aren't these van der Waals materials like graphene, okay? But because they're really strongly bound in all three directions, we can instead even put just one plane of atoms down on a substrate and construct this two-dimensional layer, this two-dimensional material, in a material where one could not get that from kind of a top-down synthesis approach. Okay? So you could think about broken symmetries or reduced dimensionality in all kinds of materials, even ones that don't want to form this monolayer structure like graphene. And since you work on graphene, I'll say I do have a project with Jenny right now trying to make graphene, but with bismuth atoms and tin atoms, so bismuthine and stannine. And those are also materials that one cannot exfoliate, but we can try to play with how we template them on a surface and kind of make them through this kind of top down.
Oh,
Yeah, we deposit it on like a hexagonal surface, and it hasn't worked yet, so it's okay. But yeah, okay. Another one, kind of, we can play with chemical potential offsets. So this is some of the electrostatics at the interfaces, so that we can play with and kind of modify things. Another one is this epitaxial string. So if I take a material that wants to have atomic spacing of 3.9 angstroms, and I put down on it a material that in the kind of ground state wants to have 4 angstroms. In the ultra thin limit, it'll kind of form this cube on cube. It has more energy to relax at the interface, what have you. And you can actually stretch or squeeze materials by, 5 or 8 or something like that %. And that's really cool because these are ceramics. This is basically like pottery that we're making, that kind of material. And if you pottery and you try to pull on it, you can definitely not stretch it 10% before it cracks, right? I mean, this is a mechanical engineering question, but it's not going to stand up. It's not even going to get 1%. You're going to get fraction of a percent that you can actually expand it before you just have fracture, okay? And compressing it as well is also tricky. So these materials we can stretch and squeeze by large percentages, and changing the atom spacing for people in my solid state class, changing the Hawking parameter, okay, can have fundamentally distinct properties that you might have in that adjacent material. And so it's really cool. Materials that are non-magnetic, if you stretch them a little bit, you can make them magnetic. I mean, you can fundamentally change properties by this idea of just moving atoms closer and further apart. Okay. Proximity to functional bases. So this is another thing we're very interested in. So we're interested in kind of these broad ideas. If you take a superconductor and you take a ferromagnet, and you squish them together. If you take a topological material, a superconductor, and squish them together. But kind of these ideas of mix and match. So instead of searching for a topological superconductor, you can search for a topological material and a superconductor, and then glue, and then hope with the interface that you would get topological superconductivity, for example. So this is also very powerful to be able to think about kind of breaking up some cool property that you want into kind of components and trying to then search for that property of the interface. And then also, I'll show you at the end, a big part of what I actually work on is these metastable bases. So actually making materials that are not the thermodynamic lowest ground state energy of the material, but whereby we can template these materials using this approach. So making a material that like wants to be cubic, we can make it hexagonal by just putting it on the right template. So we can fundamentally change how the atoms want to arise in this thing. Okay, is there any questions? This is kind of like a high level overview, and I'll go to how we do it. also interrupt me at any point, but just. Okay. So first of all, I want to say that this whole stacking atoms, really easy to do in PowerPoint. Okay, right? Really hard to do in the lab. So most of the rest of the talk, I want to show you how we do this in the lab. But anyways, like this, right? This idea. Okay, I'm going to stick the atoms on top. But we really want to do this, and we really want to do it in a very clean and ultra pure way, where we don't have kind of intermixing, we don't have other disorder, we don't have things that mess up. Because a lot of these ideas really require like very, very clean interfaces where you don't have a lot of secondary reactions or kind of other stuff that's happening. So we're really trying to do this in a very kind of pure way. Okay. So first of all, I'll just show you that indeed we can do this. So this is, okay, this is not looking good on this screen, but that's, you have to trust me, there's dots here, okay? Sorry, it just looks like a blue. Bob, I spent a lot of time on this picture and in the lab, not the PowerPoint slide.
Can you blow up your PowerPoint board? Full screen?
It's full screen on my screen.
Oh, maybe I'm not.
Okay. I think it's the projector, it's just the color is not very good. Okay. But you know, we spent so much time on this, and then it's like you take 20 years off the microscopy with a bad projector. It's frustrating. Okay. Anyways, all right. So this part down here is the substrate. So Kane is working on this one, strontium titanate. So it's one of our single crystal substrates. And then this is the type of material that we have made through this technique. So this happens to be strontium manganite, lanthanum manganite. So these are two of these different perovskite oxides. And you can see here that we have made what we call a super lattice, where we put down 3 layers of this, and then 6 layers of this, and then 6, and then 3 in various different orders. And I'm going to show you on the next slide that the properties of this system are exquisitely dependent on the layering of the material. So even if you work in a 2-to-1 ratio of atoms, whether you do 4-2, 4-2 versus 6-3, 6-3, you get fundamentally different properties of the material. So that's kind of a cool thing. But I just wanted to show you at a very high level that using these techniques, indeed, we can construct these interfaces, and we can layer these materials atom by atom by atom, layer by layer. Okay. So this is just one vignette that I wanted to mention of these types of materials to kind of maybe summarize this type of approach. So the idea here is that you can start with 2 materials, lanthanum manganite and strontium manganite. Okay. Both of these materials are insulators. Okay, so these are not conducting materials. You have 2 insulating materials, and both of them are non-magnetic as well. They're anti-ferromagnetic, which means microscopically spins go up, down, but there's no net magnetization. If you mix together the atoms in a 2-to-1 ratio, you get a material that's both a metal and a ferromagnet. So this thing would stick to your refrigerator. Okay? So first of all, this is just kind of the bulk chucking all the atoms in a can. Okay? And there's been a lot of theory about this, and we now sort of understand this material. If you're kind of do your high school chemistry, if anyone knows these elements, lanthanum has a valence state 3+, oxygen has 2-, so manganese has 3+ in this compound. Strontium has 2+, oxygen has 2-, manganese has 4+. So it's kind of known that when you have this mixed valent compound, manganese 3.3+, the bands are partially filled, okay, and you're going to have this metal state. Okay, so that's been known now for some time. What's really cool is that now let's not just chuck all the atoms in a can and shake with a 2-to-1 ratio, but let's layer these atoms and see where do we cross over. We know that this material is an insulator and this material is an insulator, but at the atomic scale, if you start to combine A plus B, is the solid, is the solution behave like all the atoms are mixed together or like the constituent parts? And so the cool thing is that we found when you layer this compound 2-1, 2-1 or 4-2, 4-2, you indeed got a property that kind of looks like the atoms were all mixed together. And maybe you can understand that, even though we ordered the atoms into these rows, in fact, you know, every time one of these red atoms is right next to a turquoise one, maybe it does behave as if they're all shaped together. But what's really cool is as soon as you go from 4,2 to 6,3, so just adding one more atom layer, you get something which is an insulator. And that was actually not understood at all, because it's thought that, kind of theory would predict that always at this interface, well, it must be metallic, because that kind of behaves like the mixture at the interface. This material is still magnetic, ferromagnetic, still stick to your refrigerator, even though the two parent compounds in that limit is the non-magnetic reagent. So you kind of get something that you didn't have before from the mixture, and you get fundamentally different behavior just by changing the number of atoms by one, with the same total chemistry, but just the layering periodicity that you did. So I won't go into the details of this, but the only thing I wanted to say is that we're not just kind of mixing things together, shaking up atoms and seeing what's happening. We're also deeply probing the quantum mechanical interactions of these materials. So for the few of you who I've seen that I know take physics 195 or know solid state physics, this is mapping out the band structure of these materials, but we're actually able to peer into the quantum mechanical interactions of these materials and understand from quantum mechanics kind of how electrons interact in this material to make an insulator versus this material to make a metal. So I really do want to say we're not just kind of mixing things together and then seeing what happens macroscopically, but we can also peer into how electrons interact via the Schrodinger equation, via quantum mechanics in this material, and then be able to understand these macroscopic properties. Okay. Those of you who that meant something to, you can also read the paper. You want all the details of that. Okay, so I just wanted to kind of summarize this approach is that we can synthesize materials with atomic scale precision. We can map out the location of all the atoms with picometer resolution, so we can see where the atoms are to picometers, and then we can both probe these kind of macroscopic properties, but also really understand at a microscopic scale kind of why things behave like they do. And then, of course, once we understand this might feed back into synthesizing some new compounds if we wanted to further try to engineer the material. Okay, so that's just kind of like the high-level approach that we're measuring things, but then understanding why they behave like that, and then kind of using that understanding to refine ours. Yeah. It's slightly different. So there is, so there is some slight strain to some of the states, but that's since our solid solution, since these ones here have the same ultimate chemistry, the same strain would be, for example, applied to the strontium manganite case in both cases. So they do have slightly different lattice constants, but that's not thought to be the origin of this kind of distinction. Yeah, that's a good question. Yeah. Okay. All right. So I want to show you just now kind of how we do this, actually the nuts and bolts of like what this looks like in the lab. So how we spray atoms and like make these types of things. Okay. Okay. All right. So this is kind of a cartoon schematic here of what we have. So as I mentioned, this technique is like atomic spray painting. So we're basically spraying with individual atoms. So in this case, we have what we call fusion cells, okay, which are these atomic scale kind of spray cans. In a prior example, we would have had one with lambda, one with strontium, and one with manganese, whatever elements are in this project. Then we just heat up the elements. And so we do this with thermal evaporation. So we just heat the material up until atoms start to thermally evaporate off. Okay. So it really depends on the different elements that you have. Some elements, you'll start to get large amounts of thermal evaporation and maybe 300 C. Other materials, you need to go to 1500, 2000, or even some for refractory metals, much higher temperatures. So it really just depends on the individual element. So this is where I mentioned to the people who are here early, this is a quote unquote megabucks evaporator. This is thermal evaporation, same thing as a puddle evaporating in the sun. But what's really special about this is that we have exquisite control over the temperatures of these various different elemental sources. So we can keep the rate that the atoms evaporate off extremely consistent, in fact, consistent over days while we optimize things. And then right here, you can see that we have a little plate, a little shutter in front, and then we're just opening and closing these shutters, which allows us to controllably deposit one atom plane and then one atom plane, and then one atom plane. And we do this all in an environment of oxygen, so that's just the oxygen that's coming in here. And in some cases, we actually do it with ozone, O3, which is extremely reactive. It says reactive is TMT, but allows us to oxidize compounds that are not readily reactive. So this is that. So here we have a spot here. This is a heater, so we can also heat our template. And we deposit the atoms on a single crystalline on a substrate template. So we're spraying atoms on a material that has the atomic arrangement that we want to impart into the substrate. So that part of it's also a big challenge. That's something Duquesne's working on, is really getting our substrate template, our kind of canvas for this spray painting experiment as good as it can be, and then we are able to spray onto that. And then we can also watch this. So this is, it says read dot, okay, yeah, electron dot. Okay. But then we can also watch this and be able to tinker with it. So it's not just kind of put it in there and then 20 hours later see what happens, but we're kind of watching this happen and we can tinker with it and optimize it during the deposition. Okay. Yeah, so if you want to come, this is on the 7th floor of the Lisa building. You can stop by, take the elevator to 7, look in the window. This is what you'll see. And so these is two of these MBE chambers. Okay, so we have two separate ones. So multiple different projects going on at once, but they're mostly the same chamber. This middle thing is actually probably the most boring aspect of the experiment. This is just a big can, and it just is for transferring the samples. So our experiments happen in what we call ultra high vacuum. So we evacuate almost all of the air from inside the chamber. This room is 760 torr. We go down to 10 to the minus 9 torr. So there's 10 to the 12, one atom in 10 to the 12 is remaining inside of our chamber when we do our experiment. And so if we want to get our sample in or out, because we want to make some measurements, of course, we don't want to vent the entire chamber and then wait days for it to pump back down. So we have this vacuum can in here, and on the back, we have a small load block, which is the same kind of premise. If it's really cold out, you go to a restaurant, they have like the double doors, so you don't blast all the cold air into the people who are eating, right? You blast it into the little room and then, you know, right? So same concept where we have like a little volume that we can kind of put the air into and then evacuate it very quickly. And then this is just has a robotic arm here that can transfer it into either. Yeah.
Is this like a clean room you guys work in, or do you all suit it up, or I don't know, it seems pretty
Yeah.
self-contained too, so.
Yeah. That's a great question. My group, so this box behind it, this white box, it's a quote unquote clean room. It's a cleaner room. There is a HEPA filter. They're very happy about that during COVID. So we do want to try to get most of the dust off, because if we load a sample in there, there's a lot of dust on it. That's not good. We start to rain the atoms down on it. So we don't have kind of a full clean room suit on. You know, we are kind of pumping things down. Everything is sort of self-contained, but you can certainly find lots of MBE fabs where everyone's wearing a full suit. Just not in my lab. I was doing the booty thing for a while, and then COVID hit and had to do the masks, and I was just kind of like too much. So I just gave up on it. You know, it's just too much. Too much. I just had to pick my battles. So, you know, but we were doing the booties because, you know, the outdoor, the salt and stuff in the roads. Yeah.
If you find a material that's really interesting and like you think that like, okay, you see the material, you're like, wow, this could solve XYZ problem. Do you have method like transferring this kind of individual atom by atom construction to maybe larger scale manufacturing?
This is a really good question. Yeah. Okay. Yeah, this is a really okay. It's not a flattering question to me, Ben, but it's a good question. It's right.
Thank you.
Okay. So first of all, so these things, as I mentioned, these MBE chambers, they are used commercially. So this is how we make blue LEDs. This is how we make various different things. So there are these commercial chambers. They mostly operate in the different regime that Professor Westervelt mentioned at the beginning, where they're kind of this self-limiting growth, not this like spend a week optimizing the growth kind of method. There are cheaper ways to manufacture materials. There's pulse laser deposition, there's sputtering, there's chemical vapor deposition, there's ALD. So I definitely would hope some of the materials that we discover, we want to really understand the intrinsic physics. But once we understand the intrinsic physics, hopefully there's methods that you can make these kind of more at scale and more cheaply and kind of with less precision than this. But if you can't, then it is possible to make things kind of at commercial scale. It just would have to be a very niche application. Some of the most, the best solar cells are made with this MBE technique as well. They don't put them on roofs because they can't make them at scale, but you know, for certain specialized applications on spatials or something like that, some of the very most efficient solar cells are made this way. So it's not impossible to imagine that you could scale this up, but your point is a good one, that ideally, if you want to make this at scale and make this cheaply, you would find another way once you've learned all the fundamental physics about it.
Kind of related, but this is done running, how big of a sample?
Yeah, this is good. So we load a sample in on a plate. This chamber is built for a 4-inch wafer, so something like this. The problem is that most of these oxide template substrates we have are already super expensive, even if you buy a centimeter by a centimeter. And sometimes we even grow on little small fractions of that because they're so expensive. So we are often, when we're just kind of testing materials, growing it on 1 centimeter by 1 centimeter laterally is more than enough for us to make our measurements, to measure conductivity, to do electron microscopy, whatever we want to do. So most of the time, that's what we're working on. Although, in principle, if you brought me a 4-inch silicon wafer, I could put that into the chamber, like on the holder. That's what it's made for. So that's sort of the aerial distance is like that thick. And then how thick it is depends on the research project of interest. Some projects are literally trying just 1 atom layer. That's fine. Other projects you might want 500 nanometers, which is about 5,000 atoms or something tall, or even maybe a micron, 6 meters. So we grow at about a monolayer a minute, roughly. So about 1 minute per monolayer. Rough, you know, we can do 2 monolayers a minute, but that's kind of rough order of magnitude. So if we want to grow a really thick film, then we might have to wait 8, 12 hours. So that's why we want things to be super stable. But we do have some projects working on with Marco Longchart, for example, for some photonic devices. They want a couple light in, so it has to be like wavelength of light, or, you know, so they want a micron. So there are some applications where we care a lot that we can make it thicker. But for most kind of, is it magnetic? Is it superconducting? Is it ferromagnet? Whatever. That stuff, actually, you're going to make it smaller. But they're still very small amounts. They're micrograms of material. So it's really very, like if you have something you can hold in your hand, because most of it's just the substrate you're holding. But they're very thin coatings on that substrate. Yeah.
Print the bigger films to see that the properties of materials change at all, or like?
Yeah. It really depends on the material. So some materials, like the physics is different in 2 atoms versus 3. Then in those materials, that's when we make that stack of atoms. So then we can repeat the stack many times, but just have 2 atoms in a single sheet. Most of the time when we find the properties vary when you get really thick is because our sample quality goes down over time because some of our conditions drift a little bit or what have you, weren't quite perfect, so the imperfections add up. So if we think we want to put down 1 atom sheet, we put down 1.01, 1.01, 1.01. You don't notice until like 50 atoms layer, and then, oh shoot, you have an extra layer of something like that. So most of the time when things vary based on thickness, sometimes it's fundamental physics, but sometimes it's just kind of accumulation of defects or something. So you just have to be more precise to get things out of it.
I don't know, like, on.
Just go for it, man.
Okay, yeah, if, how do you distinguish between, kind of cumulative effects of imperfections or fundamental effects?
That's like the whole PhD.
Oh,
Yeah, I mean, those are like the questions, right? Like, you're asking why does it take 6 years to get a PhD and not 1 year? Like, that's an analogous question. Yeah, exactly. I mean, and you know, the really cool thing about MBE is that this, so you asked about, okay, let's make this cheaply and at scale and commercially. This is, in my opinion, the way you can make the most perfect materials. And so all the world records for the various different thin film things, mobility and sync up, I mean, whatever, like any kind of these particular material records are almost all set by this MBE technique. And so when we do this right, we can get the most perfect materials. So, you know, when we get it, you know, we have other ways to know sometimes we get it wrong, but you know, this is what we're trying to do, is to make sure that we understand fundamental physics, not defect chemistry. So,
Is there a particular part of the equipment that frequently malfunctions? You must have said.
yeah, like
Most of their data are like.
all the parts. You don't know. No, it's one of those things that like everything, it's just the sum of a thousand little things. And if one goes down, then the whole thing goes down. So there's like some little couple right here, it's this little part, $20, little part. And it malfunctioned and it's sold by some company in England, and we had to get a new one, an overnight ship, and our whole thing is down. Just like little, like basically special screw, you know, and it was just like, yeah, I think that's the point, is just there's so many little things, and then if anything is broken, then the whole thing is broken. There's no 99%, you know, so.
Have you ever reduced it to perfection? That was at first like, oh no, and then lead it to some really,
Yeah, exactly.
Okay.
Yeah, that's the whole other project that I mentioned at the very beginning title slide. That was exactly it. We grew a bad sample. The bad sample behaved better than the perfect one. And then we said, okay, but let's figure out why it's bad, like what's in there. And that's what led to that whole project. So absolutely, yep, that can happen. Yeah. Okay. I don't even know what I have on the next slide. I'm sorry, I forgot. Oh yeah, just a zoom in. Sorry. Okay. Yeah. So this is just a unit. So each of these, as I mentioned, is these cans, these thermal evaporators that have each of the elements in them. And so we have wires going in them. So it's resistive heating, same way the toaster oven works. So we're just very finely controlling the heating of these cells. And then we have thermocouples and what have you that are going in here that we're monitoring. And then, as I mentioned, the row above is the shutters. And then this is also kind of cool, the oxygen. We can control the oxygen in the chamber very precisely as well. So that's it. Okay. Oh yeah, so I think, how long is this class go? I'm sorry.
Oh, about.
Okay, so I mean, I could keep talking for the next 3 hours, but maybe I can answer some more questions. Because we have lots and lots of individual projects, but hopefully this gives you some big picture overview of the stuff. Yeah.
I have two quick questions.
Yeah.
So, okay, so these structures aren't really natural in nature, right? So are they stable, generally speaking?
Yeah. So that's a great question. So it really depends on the material. So when you say, are they stable? Are they stable in air? Are they stable at high temperatures? Are they stable over time? Like lots of things can go wrong. But yeah, so some of the materials that we make, one of my students is making materials that aren't stable above 300 C. They're stable in air. They're not stable if you chuck them in a cup of water. So they immediately decompose. So different materials have different stability. Oxide materials can be extremely robust. A lot of these materials are materials like you should hopefully want to make, you know, kind of solar cells and that kind of stuff out of. And usually once you put the atoms in these precise arrangements, they don't rearrange. They're kind of stuck at low temperatures. They're not going to diffuse around and form something else. But some of the materials we make certainly could be air sensitive, could be, you know, sensitive to moisture or something like that. Yep.
When you say low temperatures, you mean like normal temperatures?
Yeah. So most of our materials are, I mean, we are stable at room temperature, but some of them, if you heat them up, they'll decompose. Yep. They'll all decompose at some temperature, but
Yeah.
some of them decompose at like the temperature of a hot plate, not or like your oven at home versus like lab high temperatures. Yeah. Go ahead. Yeah.
Do you, okay, like, again, kind of random, is there any like, can you get any interesting properties with the science that you're studying that, like, may actually be able to be reproduced with like equipment that people might have, like, not necessarily at home, but like,
Yeah.
sorry, yeah.
Yeah. So I guess, so first of all, I mean, MBE of itself, there's 4 Nobel Prizes that went for MBE, including the last one a few years ago for the blue LEDs. So certainly it is a commercially relevant technique. Most of the materials, kind of the processes that we're doing, it would be this kind of stuff, this atomic scale precision is pretty specific to what we do. but you can make coatings of materials. So there are different ways to do solution-based epitaxy. You can dissolve materials in a liquid, you can dip a substrate into the liquid, and you can cook it on a plate, and you can get stuff from that. I will say at a kind of medium scale, I mean, more expensive than a car, but like about the same cost as your Harvard education. You can buy a sputtering chamber that, whatever. So there's one of these in the CNS facilities downstairs. So there are smaller scale implementations of this that my group can use as well. So this one's pretty large, but there are kind of more modest, like would fit on this tabletop, for example, experiments that you can do at scale. Some of these as well. Yeah. Yeah.
How mature of a technology is NP? Like, is it something that like it basically is like the same level of reliability for a while, or is it something that like it like they're being
Yeah. I think that there's some advances. So this is kind of a new cell with the bellows and the differential pumping. So there's definitely some things that people are doing. Some people want to heat the substrate super hot, so they're actually firing CO2 lasers at the material and doing laser heating, as opposed to just heating it like with resistive heating, like the toaster idea. So that's a really cool idea. So there's some modest things that are happening, but I would say that to first order, the equipment has been similar since the 70s and 80s. Of course, there's been improvements over time. I should say this tool looks like one in the 80s, but I would say that the most innovation in the field is what materials do you want to make, why do you want to make them, and what are you going to measure about those materials? And that's really what's driven the field a lot. It's not that the technology is changing. So I am making materials in my lab that somebody could have made in 1995. They just didn't know that was interesting. So I would say that it's not so much that it's just an arms race to have some new technology, but I would say that it's most, I mean, we have really advanced technology, full computer control, it's more fun than the 80s, because you just press a button instead of manually do something. But really the functionality, it's not that it's changed so much since the 90s-ish. They've been working on the Cooper since the 90s. That's really where a lot of the stuff kind of took rise, but it's mostly just what problems are interested in. And to me, that's one of the things being kind of a young-ish person, older than you all, but sort of young, is that it's such a versatile technique that I really love making materials because, I can make computer memories, I can make solar cells, I can make fundamental, you just do so many different things. And you're not just on like one problem for 40 years with one technique, but even with this common technique platform, there's such a diversity of problems. And looking over some of my advisors who've been in the field for 30+ years, they've studied just such a wide range of problems in that time, but with 20-year-old chambers, so relatively constant technology.
What is the error rate for materials made with MPE? And like, what are some of the detection methods for?
So state of the art is about 1% control. You can do better than that when you have specialized growth techniques like this monolayer, the absorption control. But when you're really just kind of at the hit and stick, about 1%. So we do have various things in our lab. We do X-ray diffraction. It really depends on what the materials are. Sometimes measuring the transport is exquisitely sensitive. You have a metal insulator transition and it drops 50 degrees if you're slightly off composition. So sometimes there's various different techniques like that. Transport is a powerful way to do it, but you can also, just structural measurements as well. Yeah.
You mentioned that you designed a lot of material applications, solar panels, more efficient computing. Were there any like particular examples of materials that you where like noticed a property that?
Yeah. So we made a new material that is the first material that is ferroelectric and ferromagnetic at room temperature. So ferromagnetism, that's like refrigerator magnets sticking to the wall. Ferroelectrics come from having electrical dipoles in the material that are all lined, such that there's a net electrical polarization, even in the absence of an electric field. So most materials apply electric field, you can polarize it slightly, how capacitor works. But in these ferroelectric materials, they have that net polarization without an electric field. And it was recognized in the 70s that there was this so-called kind of contradiction between ferroelectricity and ferromagnetism, which is just a materials limitation. Ferromagnets were materials in kind of the middle of the periodic table with half-filled D shells like iron and cobalt and stuff like that. And ferroelectrics are materials with full D shells or empty D shells like titanium that often gave these displacements in the vacuum. So we discovered the first material where these two properties can coexist at room temperature. There have been a few materials where they can coexist, but at 10 Kelvin or something like that. And so that was a really cool discovery. We did a lot, that was the first slide. I showed a lot of fundamental physics, but then we got talking to Intel about how you could make a memory device out of this. And the idea would be that you could flip the ferroelectric polarization with a voltage, but then it would flip the magnetization. So you could kind of store memory in the north pole, south pole of a magnet, but control it through this voltage. And that was kind of a really cool property and kind of a new material that would be, you know, I mean, you can't buy it, it's not in the Intel chips or something like that. I don't want to sell it like that, but it, you know, it really can have very direct connections, even over time scale of like 1 PhD.
The recipe differ by
Yes. Yeah, the different materials and all of that. Yeah, so this is just, that's what the students also spent 6 years doing. It's just tinkering with the small recipes for the various different materials, substrates, all of that. Yep.
because the stacking, for instance, technical facts. So, the function makes the substrate is
Yeah, it really is material specific. Sometimes yes, sometimes no. Yeah, so that's not very satisfying, but sometimes it just immediately translates to the other one, and sometimes you do need to. Yeah, I guess we can let everyone go, but you know where to find me. I mean, some of you know where to find me, Jefferson 356 at 3 p.m. on Mondays and Wednesdays, but also you could come find me in my lab, and I'm happy to show you the experiment and just answer any questions. And you can also talk to the students because we have a dozen projects going on in our lab, so if you want to hear more details about specifics.
Great, well, thank you so much.
Yeah.